This video file was recorded in Sabunja University during recitations for the CS204 Advanced Programming course as it was given in the spring semester of 2017.
Hello guys, you have your midterm on Saturday, so you should know that we're going to solve some midterm questions, but before that we're going to see some bitwise operations. Namely, you remember from last week that we did some number representations, 1s and 2's complement. So we're going to see why, actually we saw why did we need them, namely all computers use 2's complement to represent numbers. We saw it why, because of the overflow issues, blah blah blah. Today we're going to see some bitwise operations. What do I mean about that? First, let me remind you about logical operators and or. We have others, but we don't need, I'm not going to cover others. So, if we have here 0, 0, 0, 1, 1, 0, 1, 1. 0 might stand for false, 1 for true. And I'm trying to find the AND. So this is AND. And this is the OR of 2 bits, A and B. So I have here A and B, I have here A or B. 0 and 0 is how much? It's 0. This is also 0. This is also 0. This is 1. 0 or 0. This is 0. This is 1. This is 1. This is 1. Okay? But I'm talking about bits. Those are not Boolean variables. Those are bits. That's why I don't have here and, double ampersands, okay? Or double vertical lines. I have only one. And we're going to see why. For instance, let's say that for the scope of CS204 I'm taking attendance. And we have like, let's say, 8 weeks. Let's say during the summer, so the time is kind of shortened. And I should have 1 or 0 for each of you, even you are present or not. Okay? If we do it with Boolean variables, one Boolean variable, how many bits does it have? It can be done with 1, but unfortunately, the way the C++ works, it cannot allocate less than 8 bits. Okay, so yes, you should need 1 bit for Boolean, 0 or 1. But unfortunately, when you declare a Boolean variable, you reserve 8 bits. So when you say true, it's basically something like this, 0, 0, 8 bits of zeros. Okay, so these are Booleans. Or if I say true, I have 8 bits of 1s. This is an efficient way of using things, because I can use only 1 bit. Now imagine I want to do something like this. I'm taking attendance, and I have only 8 weeks. For each week, for each of you, I should do 0 or 1. Is this better? Of course it is better. So I can do it only with 1, let's say Boolean, bool, attendance. Or I can do something like this, bool, attendance, and define an array of bools of 8 elements. Which one is more efficient? Of course this one, but this one is harder to manipulate with. So instead of, let's say, not in all of Turkey's, all of courses, blah, 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 I have a lot of students that are taking a course, and instead of using 100 gigabytes for them, I'm using 800 gigabytes because of this way of doing things. Because here I have only 8 bits. Here I have 8 multiplied by 8, it's 64 bits. Okay? This is better. But of course this is harder to do. Because here, attendance 0 is for the first week. Attendance 1 is for the second week, and so on. But here, first bit is for the first week. Second bit of that Boolean is for the second bit, for the second week. Third one is for the third week, and so on. Up until now, we didn't have to deal with bitwise operations, but here now we have to do that. And what do I mean by bitwise operations? Let's say that our computer works with 4 bits. By the way, today computers work with 64 bits. That's why if you have heard 64 bits computer, that means that the numbers are represented with 64 bits, operations, whatever. I mean, I'm not going to confuse it with this stuff. Let's say that A is an integer, and its value is 0, 1, 0, 1. Okay? I have another integer b, and its value is 0, 1, 1, 1. 2's complement, all of them, because the computer works in 2's complement. Now I want to find a bitwise AND b. This is not normal AND, ordinary AND we have seen, with double ampersands. This is bitwise AND. What do I mean with this one is the following. So the result is this one. For each of the bits, I see this staple, and put to the corresponding place the result of the bitwise operation. So I have AND. 1 and 1 is how much? That's 1. Okay. I have 0 here, I have 0 here, I have 0 here. Okay? Oh, I'm sorry. 1 and 1 is also 1. This is 0, this is 0. Yes. If I have A bitwise B, or B bitwise OR, what do I have? I have 1 here, I have 1 here, I have 1 here, I have 0 here. Okay? We have negations, but I'm not going to cover that stuff. This is actually how it works in hardware, in programming, okay? You can program it. When you write something like this, that means bitwise AND. It works not only for integers, it works for unsigned integers, for characters, for whatever. Okay, but we are going to see it for integers only. So, the first operations we saw are bitwise AND and bitwise OR. Now let's see shifting. Let me write numbers here. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so this is bit representation. This is the number, let's say unsigned. What is the value of 0, 0, 0? It's 0. 1, 2, 3, 4, 5, 6, 7. Now can you see a difference between a 2 and 4? If I had 8, let's say, it will be of course 1, 0, 0, 0, 0. So this is 8. We saw it last week. Let's say that our computer works with 4 bits. Even if I write 1, I should put 3 zeros because it has 4 bits. So this is our 4-bit computer. And actually, the first computer was 4 bits, if I'm not mistaken. You see 2, I represent it as 0, 0, 1, 0. What about 4? I represent it as 0, 1, 0, 0. What about 8? It's 1, 0, 0, 0, 0. So what has happened? It's kind of this one. It's shifted here. And in a way, when we shift this one from one place to the left, it's like multiplying. 2 multiplied by 2, it's 4. When we shift this one here, and I have 1, 0, 0, 0, it's 8. So 2 multiplied by 2, it's 4. 4 multiplied by 2, it's 8. Does it work only for 2, 4, and 8? No. Let's say it for 3. If I shift it, those 2's, I shift them here, I get 1, 1, 0. 1, 1, 0 is 6. So 3 multiplied by 2 is 6. It works. Let's see for what. Okay, again for 1. 1 multiplied by 2 is 2. So 1 comes here. Let's see for 3. We saw it. For 4 multiplied by 2 is 8. So it works for all of them. Not for all of them, for any number. Any number of bit, it works. That's why we need this stuff. This is called left shift. Okay, we shift the numbers. By left shifting, this is what we mean. I'm going to erase this part because we don't need it. So let's say I have 0. These are unsigned. Unsigned means they're all positive. When I shift it to the left, so let's say this is A. If I do something like this, that means I'm shifting all of the bits to the left by one place. So the result of this guy will be A is equal to what? Can you tell me? Okay, apparently we have 4 bits. We should have 4 bits here. So this guy comes to the first position, then 0, then 1. But what are we going to put here? What do you think? 0. You might figure out why. Because this is 5. Multiplied by 2, this is 10. Okay? But another way of doing things is the following. Always, when you shift to the left, at the end you append zeros. It's always like this. Okay? It's like when you have 32 and you shift it, you have 320. This is multiplied by 10. Because this is the decimal system. But we are working with the binary system, so we are multiplying by 2 here when we shift the numbers. Yes? Very nice. Yes, nice question. So you attended the lectures or not? That means that you are smart. You figured it out yourself. If we are working with something like this, 1, 0, 1, 0, okay, and this is 2's complement. This is a negative number, okay, and we are shifting. What are we doing here? 0, 1, 0, 1. But is this okay or not? That's apparently an overflow, yes. So if we do something like this, then B will be 0, B will be 0, 1, 0, 1, 0, 1, 0, and another 0 in the end. But this is overflow. It doesn't work. Anyway, whether the number is positive, like this one, and I know it's positive because the most significant bit, the one that is to the most left side, here, the most left bit, is 0. And with negative bits, always, when we shift to the left, we append zeros at the end. So far, so good. Let's see what happens when we shift to the right. So let's say I'm having, again, A is equal to 0, 1, 0, 1. And I'm shifting to the right by 1 position. This one here means that I'm shifting by 1 position. If I have 2, I'm shifting by 2, by 3, by 4, and so on. Okay. What will be the result of this one? What do you think? An idea? I'm shifting to the right by 1 position. So this 0, I'm shifting everything. Are you sure about that? Let's see. This one, in a way, goes out. So 0 comes here, 1 here, this 0 comes here. Now the issue is what we're putting here. If this is a positive number, I always put 0 here. Like in decimal notation, 320. So if I shift left, if I shift to the right, I'm dividing by 10. So 320 is going to be 32. Even if I have 325, if I shift left, I have 32, since this is integer division. Okay? And here it applies the same logic. This is 5. When I shift left, I have 2. This is 2. 0, 0, 1, 0 is actually 2. Okay? So 5 divided by 2 is how much? 2. In terms of integer notation. Yes? 0, 1, 0, 1. Yeah, when we shift left, we multiply it by 2. When we shift right, we divide by 2. Here it doesn't make sense because we have only 4 bits. And it is an overflow. Yeah, that's why you get an overflow. It doesn't work. So it was only for 3 shifts here, actually. You cannot do more. Okay? Or maybe 1 shift, if it's close to, you will see the overflow line later on. It doesn't always work, but if you have 64 bits, usually it works if you shift it 2, 3, 4 times, something like that. Okay. So this is when I have a positive number. Let's see when I have a negative number. So B is equal to what? 1, 0, 1, 0. And I'm shifting B to the right by 1. What is the result? Okay, so 1, 0, 1 will be here. It's okay. But what should we add here? 1. Because this is 2's complement and these are negative numbers. Okay, this is a negative number. And when I divide the negative number with 2, I'm getting a negative number. That's why I put 1 in the end. Here, we put zeros when we shift left. But when we shift right, if we are dealing with a negative number in 2's complement, then we add ones, okay? If I have 32 bits, and if I should represent this guy, this number 101, I'm adding 28 ones, okay? Just as it is the case here, I'm adding 28 more zeros. Here, actually. If I have more zeros, and this is a positive number, then I have 28 more zeros. But with negative numbers, we always see to the most significant bit, this one, and if it's 1, it's negative. If we make it 0, we're making it wrong, okay? This is how it works with bitwise operations, and we are going to see the bitwise and the bitwise or left shift, right shift today. But we are going to do it in a manner that computers work like this. But sometimes when you want to shift numbers, you want, okay, those three guys, let's say we're shifting them to the right. You want this one, which is the least significant bit, to come at the beginning, like a ring, you know, and to become the most significant one. We will see it today. Or you want, what? This guy, when you shift it to the left, okay, it's working actually. Or this one, you want this bit, when you shift it to the left, to come to this position here, as the least significant one. So we will see how we are going to do that. Because in computer, in terms of programming, when you do something like this, or like this, right shift, left shift, this is how it works. So this was the introduction part, the theory part that you need for our example. I'm going to erase it. I hope you understood it, or you want me to leave it? What do you want me to do? Because I'll need some space. Okay. I'll write it here in case we'll need to explain something. We'll go back to this part here. So our example will be bitwise operations. Just copy the code, paste it, and add it to the solution folder, to the solution basically. This is my code. Let me see the output first, and then I'm going to go through it. So I'm running the code, I'm getting this crazy output. Now let's see how did I get this fancy stuff. Okay. You really don't want to work in binary system. Trust me, decimal is nice for us because this is how decimal binary system looks. Okay. This might be a small number even. Okay. So let's go through the code line by line and see what are those guys doing. CycleLeft function. As a parameter, we take an unsigned integer, and unsigned is nice for us because in unsigned notation we don't have negative numbers, everything is positive. And what I just showed to you doesn't work for unsigned. So whenever you shift left or right, always in the end you have 0. Okay? So when you shift right, you add zeros at the end. No matter you have 1, well, no matter previously the most significant bit was 1 or not, you always had 0 in the beginning, okay? So what I showed you works for signed numbers. For unsigned, it doesn't work because we don't have negative numbers. That's why. So, basically for signed, you can, what do we need are those two parts here. This is what we need. Everything is positive. You don't have to care about the most significant bit. Let's see what this function is doing. It takes a reference of unsigned integer called num. And we want to cycle it. But we want to cycle it in a manner that I told you. Now, we don't want to use, we want to shift it to the right, but we don't want to use the leftmost bit, the less significant one. Because when we shift it, we lose it. Okay? Like it's the case here. So what are we doing here? I'm afraid I'll have to erase some parts. Okay, so this is my number A. When I'm shifting to the right, you see that this is wrong. Oh, I'm sorry. When I'm shifting to the right, this is okay. You see that I'm losing this one. And I don't want to lose it. I'm getting, from 101, I'm getting 10. From 5, I'm getting 2, dividing by 2. I want this one to appear in the beginning. So what I'm doing is the following. Let's say that this is my number. Let's say that I'm working in 4 bits. Although integers here are 32 bits. I'll show how it works for 4 bits. And you can expand the logic for 32 bits. So let's say that my number that I'm taking here as reference is this one, 0, 1, 0, 1. I want to cycle it. So remember, I'm writing here it as a comment. So initially, num was 0, 1, 0, 1. I want to get 1, 0, 1, 0. That's why I define another unsigned number called write bit. But this is how the write bit works. Basically, I don't want to use this write bit. I want to take it and append it, shift this guy, lose the write bit, and in the end append it to the left. This write bit is equal to num bitwise 1. Num bitwise 1. Basically, the write bit is equal to num is 0, 1, 0, 1. How do I represent 1 in 2's complement? With 4 bits. So our machine works in 4 bits. So how do I represent 1? Come on. I know it, so because it's too easy. So it is, yes, it is 0, 0, 0, 1. So what I'm doing here, I'm taking a bitwise between the number and 1. And what do I get? So this is bitwise and 0, 0, 0, and 1 in the end. I'm writing this one. 0, 0, 0, 1. Okay. Then I'm shifting the number to the left for 1 position. So when I'm shifting, what I'm getting, this guy 0 comes here, 1 comes here, this 0 comes here, and in the end I append another 0. Okay, so I have 0, 0, 1, 0, as we saw it previously. I don't have this guy anymore. Instead of this, I have 0, 0, 1, 0. Finally, in the end, what I'm doing? This guy is first executed. So I shift to the left by 31 times this write bit. Actually, this is because integers have 32 bits. But since we work in 4 bits, we're going to shift it for 3 times. So just imagine we have here 3. So write bit is going to be shifted for 3 positions. So what do I get when I shift this for 3 positions? 1, 0, 0, 0. Okay? So I have 1, 0, 0, 0. And finally, num is equal to the num bitwise or write bit. So this num is now equal to previous num, which is 0, 0, 1, 0. Bitwise or 1, 0, 0, 0. How much is this guy? This is 0, this is 1, this is 0, this is 1. Okay, and this is assigned to num. So I will have 1, 0, so this is bitwise or 1, 0, 1, 0 in the end. Okay, is this clear? Now you might say, okay, what if this num was 0? Then very nice. Okay, so you see it's working when the rightmost bit is 1. Okay, but is it working when the rightmost bit is 0? Yes or no? It is working. It's even easier. This is the most challenging part. So we didn't lose this one. We appended it in the end by doing bitwise OR. Did you understand this one? Yes. Let's go with the example when the number is something like this: 0, 1, 1, 0. It should be even more easier to understand. So, number, we take it as a reference. it is 0, 1, 1, 0. I take the rightmost bit. The rightmost bit is equal to none, which is 0, 1, 1, 0. Bitwise end with 1, which is 0, 0, 0, 1. What do I get here? All zeros. 0, 0, 0, 0. So I put the right bit here, which is 0, 0, 0, 0. I shift it 3 times, since I'm working with 4 bits. But in the logic of 32 bits, as it is represented in C++, I shifted 31 bits, meaning this guy, when I shift it, will come here, but it's the same. So right bit after shifting 31 times is the same. Of course, I shift the number to the left by 1. So number is 0, 1, 1, 0. When I shift it to the left, what do I have? I have 0, 0, 1, 1. Okay? Now I want to append the rightmost bit, which came from here, came here, but it's the same, it's all zeros, to here. That's why I shifted the right bits by 3 times, so 31, and I'm finding the bitwise OR. So number is equal to old number 0011, bitwise OR 0000, which is what? 0011. It's a sign, so it's working. Again, this is for 4 bits. The logic applies for 32 bits. This is CycleRight. CycleLeft is doing the opposite, and I'm not going to go through it. Okay? Basically, when I'm cycling left, I don't want to lose the most significant bit, so I take it and append it to the end. The logic is the same, so I'm not going to explain it. HammingDistance. Let's go to the other function. Remember, both of those functions, CycleRight, CycleLeft, as reference, as a parameter, they take an unsigned integer. So we are working with unsigned references. HammingDistance. What is that? Do you know about that? Let me tell you what's HammingDistance. If we have 2 strings of bits, A and B, we find the differences, we find the number of different bits in corresponding places. For instance, let's say A is equal to 1101, and let's say that B is equal to 0101. HammingDistance is the number of different bits in corresponding places. So here, let's check it here. Are those bits different? No. They're the same. Are those bits different? No, they're the same. What about those? No. What about the most significant bits? Yeah, they're different. So the HammingDistance, I'm going to write it as HD is equal to 1. Okay? Let's see how do we find the HammingDistance of 2 numbers A and B. Let me give another example. Maybe this is kind of weird. So I have 0, 1, 1, 0. And this is 1, 1, 0, 1. Okay. What about the first, those 2? Yes, we have one difference here. We have also a difference here. 1 and 0 are different. Those are the same. We have another difference here. So the HammingDistance of those guys is 3, of A and B. Let's see how we can find the HammingDistance between those 2 bits as it is given in this function. So we have A, which is given as a parameter. Let's say A is 1101. Then we have B. B is 0110. Inside we define C. And C is equal to what? A bitwise XOR B. Can you tell me what is this? Have you seen this previously? Yes or no? So what does this logical operator imply? Bitwise logical operator. Can you tell me? It what? Power. No.
It is 1 and 1 plus 1.
Yeah. So it's another logical operator. Let me write it here. So bitwise and bitwise, or we have bitwise XOR. Bitwise, I'm saying. When they are different, bitwise XOR is true. Otherwise, when they are the same, this is false. So 0, bitwise XOR 0 is again 0. 0 XOR 1 is 1. 1 XOR 0 is 1. And 1 XOR 1 is 1. Let us not confuse the places and the arrangement. So this is how it works. Oh, I'm sorry. Yes. Yes. But you didn't know the answer. Why are you answering now? Okay, you're right. So this is 0, 1, 1, 0. Now I'm finding the bitwise XOR between A and B. So how much is that? So this is C equal to A XOR B. 1 XOR 0, this is 1. This is also 1. This is 0. This is 1. So C, I put C here. And it is 1, 0, 1, 1. Then I'm defining another unsigned integer, which is sum. Initially it's 0. So I'm defining sum here. Initially sum is 0. Now pay attention what I'm going to do. I'm going to count those ones. Sum up those ones. 1 and 1 and 0 and 1 is 3. Because the Hamming distance of A and B is 3. Okay? And I put that sum here. So I start from 0 to 32. And I shift it 32 times. In our case, since I'm working with 4 bits, I'm going to shift this guy only 4 times. Because I want to find all those ones. And always I take the less significant bit, the one which is at the rightmost place, and add it to sum. Okay? So this is what I do. Sum is equal to previous sum, C and 1. So where is C? This is C. Sum, when I say 0, 0, when I say 0, basically I mean 0, 0, 0, 0 in binary. Okay? So I say sum is equal to previous sum, sum plus equal. So this is 0, 0, 0, 0. And bitwise end 1. And 1 is represented as 0, 0, 0, 1. What is the result of this guy? This is 1. So I say sum is equal to old sum, which is 0 plus 1. That's why this is going to be 1. I shift C to the right by 1 place. So when I shift it to the right, and we are working with unsigned numbers, don't forget. So when I shift it, 1 comes here, this 0 comes here, this 1 comes here, and what do I append in the beginning at the most significant bit? Unsigned numbers. Come on. 1. Do we have negative numbers? No, so I append 1. 0. Okay? Basically 0, 1, 0, 1. Let me write it better. 0, 1, 0, 1. Okay? You see 1 was gone, and I have 2 more, and I have to do the same thing again. Sum is 1. Again, we iterate the loop for the second time, and I say sum plus equal to this sum, which is 0, 0, 0, no. Sum plus equal to C bitwise 1. This is C, so I have 0, 1, 0, 1, bitwise 1, which is 0, 0, 0, 1. When I do the operations, I get here 1, everything else is 0, which is 1. So I add 1 to the previous sum, and I have here 2, which is 1, 0, but let me switch back to decimal. I have 2, okay? I rotate this guy again, and when I rotate again, I have 0, 0, 1, 0. Okay, so when I go here, okay, so C is now 0, 0, 1, 0, 0, 0, 1, 0, 0 and 1 is 0. Okay, so I'm adding 0 to 2, which is again 2. I rotate it again, shift it again, 0, 0, 1. So I have here at this part for C 0, 0, 1 and 1. 0, 0, 0, 1 and 1, which is 1. I add this 1 to the sum, which is 3, and I shifted it 4 times. Okay? I shifted it 4 times since we're working with 44 bits. If the unsigned integers were represented by 32 bits, we were going to shift it 32 times, and we find the Hamming distance. It was 3 here, it is 3 here. Is this clear? Okay. Finally, print to screen. When you try to print this number here, sum is not 3, actually. It's not written as 3, it's written as 0, 0, 1, 1. Okay? But when you print it, it's not shown like this, it's shown as we have seen already, as 3. So what we want to do is the following. We really want to represent this guy, this sum, as it is. And how are we going to do that? There are other ways to automatically convert from decimal to binary, and when you print it, it always prints it binary, blah, blah, blah. We don't want to go to that. It's easier, actually. We want to do something new for you, which is the following. So I have the sum, which is 0, 0, 1, 1. Let's say, again, that I'm working with 4 bits. For each bit, I'm going to allocate 8 bits. I'm going to see each of them as a character. Okay? So what I'm going to do, I'm going to allocate, I have one character as how many, we have 4 bits here. So how many characters should I allocate? 4 characters. Yes. Okay, 4 characters. But I want to put it in char array. And the problem with the char array is the following. It doesn't have limits. Okay? It's a kind of char array, is a string. And we don't have any limitations for the number of bits for strings. You can put 100 gigabytes if you want to run string. So there's a problem. How do we know when we are ending the string bit? How does it end? Because if you don't know, you're going to print all of your memory. So what are we going to do? If you didn't know, if I'm not mistaken, I told this in CS201, but I'm going to tell it here. You have your chars here, 1, 0, A, whatever. When you come to something like this, that means that your char array or your string is finished. Okay? Always watch for this character. So when you enter a string, you don't know it, but automatically the compiler appends this character at the end. You should know it because sometimes you have weird mistakes and you don't know where's the mistake. Mistake is here. If you don't have it here, you're going to print over all of your memory. Okay, so this is an important character. So I have how many? So I want all of those bits to represent them as characters, plus put this guy here. How many bytes should I reserve? How many characters should I have? 4, 5. 4 for the bits, plus this one. This is character 5. Okay. That's why our char array will look something like this. I have 0 here, 0, 1, 1, and this sign. But the problem is that each character, how many bits does it have? You remember? Come on. 8 bits. Yes. So what I'm doing, so this is 8 bits. This is also 8 bits. And so on. So this is 1 bit here, but since I want to print it, so I want to see it as 0 or 1s, and I want to show it as a character or string or array of characters, I must reserve 8 bits. This is how characters work. Okay? So 0, actually, when I put it here, this is the 0 character, but this is also a string of bits, and it's going to print the corresponding ASCII code of that. Okay? So when I put 1, is that this one is also a string of bits, but it's going to print at your screen the corresponding ASCII code. And that applies to for the last character. I know it's confusing, but you'll get used with this. This is how computer works. That's why when computers came first, they used to write ones and zeros, which was too confusing. So they came up with assembly code, which is easier. But it was easier than ones and zeros, but it was still confusing. That's why we came out afterwards with C++, like languages. Okay. If you understood this stuff, then let's go and see what I'm doing here. So, this is what I do. Size of unsigned integers is 32. So basically, I'm declaring an array of 32 characters plus 1 because of this guy here, from 0 to 33, okay, to 32. And I make the last character to be this special character that denotes the end of the array. And this is the important part here. How am I going, if I have 0, 0, 1, 1, let's say, how am I going to fill those numbers here? It's done with this for loop. It's done 32 times, because we are working with 32 bits. Here we are going to see it in 4 bits. How I'm going to do that? I start from 0. So this is my first character. 0, 1, 2, 3, 4. I put the last one to be this one. Then what I'm doing, if num at 1 is equal to, let me erase the board and let me write it better. So where's my eraser? We're not going to need this stuff. What I'm trying to do is I want to print this guy, 0, 0, 1, 1. Okay? So, this is our num, unsigned num. First, I'm doing this stuff, num and 1. Let's say this is, okay, num will be here. So this is 0, 0, 1, 1. This is our array. I don't know what do I have in it here, except for the last character, which is the special character. Now I'm filling the arrays. I'm checking. I'm finding the end of 1 in the number. So 0, 0, 1, 1, and 0, 0, 0, 1. How much is this? This is 0, 0, 0, 1. So I'm checking. If when I find the end, the bitwise end of 1 in the number, if I get 1, then the list of 31 minus I is 1. In our case, it will be the list of 3 minus 1, it's going to be 1. Okay? So what I'm doing, I'm putting basically 31 minus 1, or I'm putting the 1 here. Okay, 3 minus 0 is 3. I go again. Here in the end, I shift it to the right. So this num is shifted. And what I'm going to have is 0, 0, 0, 1. Again, I go inside the loop and I check whether the bitwise end of 1 and num is 1. So it's 0, 0, 0, 1. And 1, it's again 1. So I put 1 here. It's 31 minus 1. In our case, it will be 3 minus 1, which is 2. I'll put it here, because we're working with 4 bits. Again, in the end, I shift it to the right. When I shift the number to the right, what I'm going to have, I'm going to lose this one. Everything is going to be 0. And I'm checking. Bitwise of num and 1, is it 1? No. It is 0. Okay, so when I put it here, bitwise is going to be 0. That's why I'm saying 31 minus 2, which is 1, is going to be 0. I put the 0, 1. I shift it again, which is not going to have any change. I put another 0, and I'm done. When I print the character, I'll have 0, 0, 1, 1 as an output. But these are characters. I'm not printing this guy, actually. I'm printing the characters, the string that I got from the number. Okay? I'm telling you again, it's a much easier way to do this, but we want to learn to you how to do bitwise operations. That's why we are doing it the hard way. And remember, this is also important, the special character in the end. If this is all done, we are done with our program basically. So let's see, what do? We declare an unsigned integer a, b, we print a, we CycleRight a, we CycleRight a again with the function we saw, so we don't lose the least significant bit. We print it again. We cycle it to the right again, we cycle it to the right again, we print it, then we print b, we cycle b to the left, again to the left, we print it, then we find the Hammington distance, the Hamming distance between them. Okay, here. We print c, which is the Hamming distance. Okay, okay, and this is it. So let me show you the output again. And let's go line by line and see whether our code really works and whether we got the output we are looking for. So we print A. This is how 26, 35, 42, 34 looks like. If you don't trust me, just let's go with this stuff. Always go with view programmer. Usually it's standard, but we are not standard people, we are programmers. So go with view programmer. Let's see whether it's correct. I'm writing 2, 6, 3, 5, 42, 34, and I'm converting into binary. Let's see what is it the case here? Yes, it is. I have, you see here 1100, 1100. Then I have 100, 100 here. Then I have 1000, I have 1000 here. Again 1000, 1000, 1000 here, 1000, then 111, 111, then 010, 010. Why do we append zeros? Because we should have 32 bits. Okay, this is a positive number, it's unsigned. We append 0, so it's working. It's correct. Meaning the print-to-screen function works correctly. Then we cycle it right twice, as you can see it here, the A, but we send A as a reference. That's why the change will be seen again, and we print it. So this is the second time we print it. Can you see that it's really cycled to the right twice? You see 1, 1 here comes here, cycle twice, shift it twice. Then we have 0, 0, 0, 0. Then we have 100 and 100. 1000 here, 1000 here. It's like shifted for 2 places. Can you see it? Yes or no? Come on, you're paying attention. Or maybe it's the font is too low, too small. Okay, so again, I'm printing K. I'm cycling it right twice. Once here, once here, and I'm printing A again. So this is the first time I print A, and this is the second time I print A. Okay, and if you see, it's really like all of the bits are shifted twice to the right. Okay, and as you can see, the least significant bits are appended in the end. So in the end we have 10, and in the beginning you have 10. Okay, then zeros and blah blah blah, everything is the same. We didn't lose that. Again, we CycleRight twice again, and we print A for the third time. If you see this guy is, we cycle twice this guy, so this one, when we cycle it twice to the right, we get this output. Okay, now we print B, and it works. So this is our B. We cycle to the left twice. Let's see.